Hello my dear students, I warmly welcome you to CR Digital Classes. So in this lecture, we are going to discussing another important topic, that is the orthonormal sets. Okay, so in this lecture we are going to discussing about definition of the orthonormal sets, one theorem based on the orthonormal sets and one problem based on that condition. Okay, so one of the very important problem, Mama. Observe carefully the question first of all. Define the orthonormal set. Okay, so and also we can give the examples. Second question is, an m by n matrix capital U has the orthonormal columns if and only if U transpose into U equal to capital I. Okay, so we have to prove that condition. Actually it is a theorem. Okay, and m by n matrix capital U, here we have one matrix capital U, order of that matrix is m by n. Okay, for that matrix has orthonormal columns if and only if we have to prove that U transpose into U is equal to identity matrix. U transpose into U is equal to identity matrix. That is the second condition. And the third problem is, let capital U is equal to 1 by root 2, 2 by 3, 1 by root 2 minus 2 by 3, 0, 1 by 3. Okay. So here capital U is a 3 by 2 matrix. Okay. 3 rows are there, 2 columns are there. And we have small x is equal to root 3. X is equal to root 2, 3. X is equal to root 2, 3. Then find norm of U x. Okay. Find norm of U into x and verify that the first condition is norm U into x equal to norm x. The second condition is U transpose into U equal to 1. Okay. So this is the total question regarding the orthonormal sets. So in this lecture, first of all we are going to start with the definition of the orthonormal set. In the previous lectures we discussed that the orthogonal vectors, okay, and we also discussed that orthogonal sets, and we also discussed that orthogonal basis. Okay, and these three definitions we discussed in the previous lectures, that is orthogonal vectors, orthogonal set and orthogonal basis. Now orthonormal set. So we are going to discussing orthonormal set. Gonal is different, normal is different. Okay, so orthonormal vectors అని అంటాం, లేదంటే orthonormal set అని కూడా చెప్పేస్తాం అన్నమాట. orthonormal set. Okay, so let's start the definition first of all. The orthonormal set, that is the heading. Definition: capital A, okay, a set U1 U suffix 2 up to some U suffix P is said to be an orthonormal set. Okay, so if it is an orthogonal set of unit vector. Okay, so whenever you take a set of vectors, okay, whenever you take a set of orthogonal vectors U1 U2 up to some U suffix P, whenever you take a set of orthogonal vectors, then this orthogonal set of vectors is said to be orthonormal set. Okay, is said to be orthonormal set. But what is the condition? This orthogonal set consists of unit vectors. Okay, this orthogonal set consists of unit vectors. Unit vectors means whenever you apply that the norm of that each and every vector, that the length of the vector equal to 1. Norm or length both are same only. Okay, so norm of that given vector or length of the given vector equal to 1 అయితే we can call it as a unit vector. అంటే whenever you take an orthogonal set, that orthogonal set is said to be orthonormal. The condition is the length of vectors in that set is equal to 1, or the all orthogonal vectors are the unit vectors, then we can call it as a orthonormal set అని చెప్పేస్తాం. ఓకే, సో meanwhile orthogonal set అంటే ఏంటి? Okay, similarly we can discuss that orthogonal set. What is that orthogonal set? Orthogonal set is a set in this format only, small u1, small u2 up to some u suffix p. Okay, the product of any two different vectors equal to 0. The product of any two different vectors in that set equal to 0, then that set is called, then that the collection of those types of vectors is called orthogonal set. Orthogonal anemo only that product value equal to 0 అని చెప్తాం. ఆర్థోనార్మల్ అనేమో దట్ నామ్ వాల్యూ ఇస్ ఈక్వల్ టు 1 అవ్వాలి. దోస్ టైప్స్ ఆఫ్ వెక్టర్స్, అలాంటి వెక్టర్స్ ఉన్న ఒక సెట్ ని మనం ఆర్థోగోనల్ సెట్ ని ఆర్థోనార్మల్ సెట్ అని చెప్పేస్తాం. ఓకే, సో దట్ ఈస్ ద డెఫినేషన్ అమ్మ. సో కొంచెం లిటిల్ బిట్ కన్ఫ్యూజన్ ఉంటది ఆ ఆర్థోగోనల్ కి ఆర్థోనార్మల్ కి. సో వెన్ ఎవర్ యూ డూ ద మోర్ ప్రాక్టీస్, దెన్ యూ విల్ గెట్ ద you will not get any confusion. So therefore next point is, if W is the subspace spanned by an orthonormal set. If W is the subspace, here whenever you take a vector space capital V, okay, in that vector space subspace is there, capital W. This W is spanned by is nothing but generated by, okay, spanned by is nothing but generated by an orthonormal set only. ఈ W అనేది ఆర్థోనార్మల్ సెట్ అంటే ఇందులో ఉన్న వెక్టర్స్ యొక్క నామ్ అప్లై చేస్తే మీకు ఎంత వస్తుంది, 1 వస్తుంది. అలాంటి వెక్టర్స్ యూనిట్ వెక్టర్స్ తోటి ఉన్న ఒక ఆర్థోనార్మల్ సెట్ తోటి ఫామ్ అయింది ఆ W అనేది. దెన్ దట్ u1 u2 up to some u suffix p is an orthonormal basis, okay, for W. Whenever a subspace capital W in the vector space capital V is generated by orthonormal set, then that set is also said to be orthonormal basis for the W, and this set is linearly independent. That orthonormal set is also linearly independent. One of the very important topic adi. Okay, endukante in the previous lectures also we discussed that orthogonal vectors, here orthonormal vectors are the linearly independent antunnam. In the previous lectures also one of the important theorem we discussed that orthogonal vectors, orthogonal vectors or orthogonal set, we proved that it is a linearly independent set అని మనం ప్రూవ్ చేసాం. ఆర్థోగోనల్ వెక్టర్స్ ఆర్ ఆర్థోగోనల్ సెట్ ఈస్ లీనియర్లీ ఇండిపెండెంట్ సెట్ అని. అక్కడ ఆర్థోగోనల్ లీనియర్లీ ఇండిపెండెంట్ అయితే ఇక్కడ ఆర్థోనార్మల్ సెట్ కూడా మనం ఏమని చెప్తామంటే లీనియర్లీ ఇండిపెండెంట్. దట్ ఆర్థోనార్మల్ సెట్ ఈజ్ ఓన్లీ ఆర్థోనార్మల్ బేసిస్. ఓకే, సో దట్ ఈస్ ద డెఫినేషన్ రిగార్డింగ్ ద పాయింట్. ఓకే, సో ఆ పాయింట్ ఎందుకు డిస్కస్ చేసామంటే వీఆర్ యూజింగ్ ఇన్ ద నెక్స్ట్ క్వశ్చన్ అనమాట. సో దేర్ ఫోర్ now we are going to discussing that the second question amma. Given that here we have observed that second question, we have capital U, one rectangular matrix, that capital U has orthonormal columns. Okay, so if and only if we have to prove this condition, okay, that U transpose into U is equal to capital I. In that purpose, given capital U is an m by n matrix, let capital U has only 3 columns. Orthonormal columns unnai, బట్ ఆర్థోనార్మల్ కాలమ్స్ ఎన్ని ఉన్నాయంటే ఇక్కడ మనకు ఓన్లీ 3 కాలమ్స్. అంటే ఇక్కడ వెక్టర్ స్పేస్ మీకు ఏమవుతుందమ్మా, క్యాపిటల్ V is equal to R3. వెక్టర్ స్పేస్ క్యాపిటల్ V is equal to R3. Therefore let capital U has only 3 columns. For our convenient we are considering only 3 columns. Only 3 columns ఉన్నాయంటే ఎన్ని రోస్ ఉంటాయి మనకు అక్కడ, ఓకే, స్మాల్ m rows and 3 columns ఉన్నాయి. So therefore 3 vectors, these 3 are. So therefore u1 u2 u3, okay, these 3 are u1 u2 u3 is in Rm. So okay, ఇక్కడ Rm అనేది నెంబర్ ఆఫ్ రోస్. ఓకే, పవర్ లో మీకు స్మాల్ m ఉంది కదా, దట్ స్మాల్ m ఇండికేట్స్ దట్ నెంబర్ ఆఫ్ రోస్, అండ్ Rn అని రాసాం అనుకోండి, that indicates that number of columns. Okay, so therefore we have taken capital U is a 3 orthonormal columns matrix. Those orthonormal columns we have taken as u1 u2 u3. So therefore capital U is equal to, we can take in this format, capital U is equal to u1 u2 u3 in the matrix format. Consider, so U transpose into U. So resultantly we have to prove this condition amma. To prove that condition we are considering that LHS part. That LHS part is U transpose into U equal to, here U is a one column matrix. For that column matrix, if you apply the transpose, that column matrix will row matrix will become column matrix. Here capital U is a row matrix. First of all, capital U is a row matrix. Whenever you apply the transpose, that row matrix will become the column matrix. Rows will become the column. So therefore, this one is the U transpose value, and next into capital U, that is the column matrix into row matrix. Now you can multiply those corresponding values among. Why? Because here 3 rows are there, only 1 column, and for this matrix only 1 row and 3 columns. Okay, so therefore here 1 and this one both are equal, so we can apply the multiplication property. So therefore then U transpose into U is equal to, if you multiply that condition, U1 transpose into U1, okay, so U1 transpose into U2 and U1 transpose into U3. Okay, so therefore next to U2 transpose into U1, okay, so U2 transpose into U2 and U2 transpose into U3. So next to third row also we can write in that format, U3 transpose U1, U3 transpose U2 and U3 transpose U3. In that format we can apply that the multiplication for those two matrices. Here the entries in the matrix are inner products. Entries in the matrix, whenever you apply that the multiplication for that entries, the product, okay, the product of that entries is in the inner product format. That means a scalar product. U transpose into V equal to V, U into V is an inner product from the definition. So therefore, thus the columns of capital U are orthogonal if and only if. So U1 transpose into U2 is equal to U2 transpose into U1 is equal to 0. If you observe carefully, Amma, okay, so if you observe carefully, U1 transpose into U is there. U1 transpose into U is there. Actually, if you apply the multiplication, what you will get, Amma? If you apply the multiplication, okay, observe carefully here. Okay, so here you can observe that here capital U is a, basically it is a row matrix. Capital U is a, basically it is a row matrix, but the vectors are the column vectors. Here U1 you will exist in this format, column, and U2 you will exist in this format, and U3 you will exist in this format. Basically that vector is a row vector, that matrix is a row matrix, but originally if you imagine that vector, those vectors are the column matrices. Okay, column matrices. Then whenever you apply the multiplication for U transpose into U, okay, so already these rows will become columns now in the U transpose, then columns will become rows. Okay, these columns are the rows. Okay, U suffix 1 is not only one value, it is a row, total row. Okay, for that row you have to do the multiplication for this column. Okay, that means especially here with this U1 you have to do the multiplication. Okay, with this U1 you have to do the multiplication for, here U1 in the first matrix, U1 is nothing but it is a column, it is a row. Okay, in the first matrix U suffix 1 is nothing but it is a row. For that row you have to multiply these 3 columns. In that format only you will get in this format, U1 transpose into U1 and U1 transpose into U2 and U1 transpose into U3. Next you can see here, next row is U suffix 2. Okay, so here you can observe that next row is U suffix 2. U suffix 2 is the next row. That row we can do the multiplication with these 3 columns. So then U2 transpose into U1 and U2 transpose into U2 and U2 transpose into U3. In that format you will get that values. Here the entries in this matrix are the in the form of inner product. What is that inner product form? Whenever you take U into V, we can write according to the definition of inner product, we can write U transpose into V. Okay, U transpose into V. U into V equal to U transpose into V. Or else if you take V into U, we can write V transpose into U. If you apply the transpose for the first vector, it is inner product. If you apply the transpose for the second vector, it is called outer vector, outer product. Okay, if you apply the transpose for the second vector, it is called outer product. If you apply the transpose for the first vector, it is called inner product. So ikkada meeru deentoti match cheskondam okkasari. So U transpose into V format lone manaku unnai kada, first vector ki transpose undi, second vector as it is ga undi. So ikkada unna each and every entry, idoka entry manaku, so this one oka entry, this one oka entry, each and every entry in that matrix is in the form of inner product. Okay, in the definition form of the inner product. So therefore then clearly we can do the process amma. Inner product lo unnayante, so according to the orthogonal, and those columns are orthonormal columns. So therefore here the entries in the matrix are inner products. Here the entries in the matrix are inner products. So that means U transpose into V is equal to U into V is an inner product. Thus the columns of capital U are orthogonal. The columns of capital U are orthogonal. So if and only if U1 transpose into U2 equal to U2 transpose into U1 is equal to 0. Whenever you take that the columns of capital U are orthogonal, if and only if orthogonal ante manam em cheptamamma aa column lo unna vectors yokka product manam em ani cheppesam, that value equal to 0. So therefore U1 transpose into U2, that is equal to U2 transpose into U1 value is equal to 0. In that matrix, wherever you have these values, substitute those values equal to 0. Okay, in the previous matrix. So therefore, and the columns of capital U have unit length if and only if, so U1 transpose into U1 is equal to 1, and U2 transpose U2 into 1, and U3 transpose into U3 equal to 1. Okay, the columns of capital U have unit length. ఏ వెయిట్ కి యూనిట్ లెంత్ ఉందంటే మీరు ఇక్కడ అబ్జర్వ్ చేయండి ఒకసారి.